Okay, let me talk for a second about logarithms. We've probably all seen logarithms in our past, in our very distant past sometimes, but they're very important. It's another tool that you can have in your tool belt that helps you solve certain equations. So let's talk about those really briefly. Essentially, a logarithm is the inverse function of an exponential. So we just talked about this exponential function, y equals b raised to the x power, and we say that y is the value of b raised to the xth. Well, the inverse of that, or the logarithm, it would simply say x is equal to the power that I need to raise the base b to in order to equal y. You use this in order to find the value of x. So thinking of an inverse function, we've used these a lot. You use these every day. You just don't think of them in these terms. So if I multiply two numbers together, y equals a times x, but I need to find the value of x that gives me a certain y, then I'm going to use the inverse of that multiplication function, which is division. So I use division to find the value for x, and it'd be x is equal to y divided by a. Same thing for addition and subtraction. I have y equals a plus x, but if I want to find the value of x, then I'm simply going to subtract and make it x equals y minus a. So all these are inverse functions of each other. For an exponential, the inverse is a logarithm. For multiplication, the inverse is division. For addition, the inverse is subtraction. All you're doing is trying to solve for that x. Remember, we said the function y is equal to f sub x. Well, what happens if we know the y, but we want to find the x that gives me that y? That is all that we're doing for logarithms, and they're incredibly powerful to help us solve for these exponential functions like this. So for example, if I have 100 equals 10 raised to the x, and I want to find out what the value of x is, we could probably look at this and figure it out because 10 times 10 is 100, but we could also use this log. So log base 10 of 100, what is that going to be equal to? Now, how would I solve this? You can use a calculator and use a log function. I guarantee you, even the calculators on a phone have a log function. And all it's saying is if I do log of 100, it'll give me 2, because that is telling me the number that I would have to raise that base value to in order to equal this y value. Another one that's less obvious, what happens if I tell you that 10 to the x is equal to 5, what's the value for x? All I would need to do is do log of 5, and that would pop out that x is equal to 0.7. Now, when I see a log written like that without a 10 beneath it, it implies that the base is 10, because we all have 10 fingers, 10 toes, right? Log base 10 is very common to us. So if you see log without a subscript, that means the base is 10. Now, another one you're going to see is what we talked about in the last video, this Euler number, e. And so let's say I have this equation 1 equals e to the x. What's the value of x? And so this is the same thing as saying log base e, because that's that number, 2.718 whatever. And what do I have to raise that to be equal to 1? Now you'll see, instead of seeing this log e, you'll always see it this way, ln, natural log. So if you ever see ln and a number in parentheses, that means you're taking the natural log of it. And the ln of, or natural log of 1 is equal to 0, because that's the only value of x that would give me an e to the x equal to 1. Okay, similarly, let me just clean this up just a bit. There. If you have e equals e to the x, you should actually know this, because to a value to be equal to itself, you have to raise it to the value of 1. But this is also saying that the natural log of e is equal to 1. Okay, so this seems kind of theoretical and abstract. Why do we use this? Because it's very powerful. It helps us solve things we wouldn't normally be able to solve. And it has 3 really nice properties. And let me state them quickly and show you examples. The first is that the log of a product of two numbers is equal to the sum of the logs of them individually. So the log of x times y is equal to the log of x plus the log of y. It turns a multiplication into addition. Very powerful. Similarly, the log of a number divided by another number is equal to the log of the first minus the log of the second, right? Log of x divided by y is equal to log x minus log y. In other words, it turns the division into subtraction. And third, kind of makes sense here, is that the log of a number raised to another number, log of x to the 8th power, is equal to a times the log of x. In other words, the power becomes a multiplication. So what does this let you do? It lets you solve things, by breaking them up. And this will become powerful if you have very complex functions, and we will in later times. So you can see that the natural log of 3 times 5 is equal to the natural log of 3 plus the natural log of 5. You can try these on your calculator. Natural log of 12 divided by 7 is the same thing as saying natural log of 12 minus the natural log of 7. And the natural log of 3 raised to the 6th power is the same thing as 6 times the natural log of 3. And finally, natural log or log, you can do either one. It doesn't matter what you want to do. The logarithms have the same property. Okay, you're probably saying, yeah, that's great, but who cares? Well, let me give you an example of where you can use this. And we will use this later on, especially when you want to look at a complex equation or function and make it a little simpler. So here's a simple question. Suppose I invested a sum of money and it has an interest rate of, let's pick a number, 7% annually. How many years, T, will it take for that investment to double in value? Okay, so we think about this, and I know from our previous lecture that the future value is equal to the principal, the amount I put in, times 1 plus r, that interest rate, raised to n, where n is the number of periods. So if I have a 7% annual, my n is in number of years. And I want to find it where the future value is worth twice the original value, the principal, when does f equals 2p. So what am I going to do? I'm going to substitute in, okay, when does f equals 2p equal p times 1 plus r to the nth? Now I want to simplify this. The p's cancel out, and I end up with 2 equals 1 plus r raised to the nth. Plugging in the r is 0.07, I get this. The 2 equals 1.07 raised to the nth. How do I solve for this? I want to solve for n. Hopefully this looks familiar. It's an exponential function. So I can do this by solving or transforming both sides. So I end up with the natural log of the left side, natural log 2, ln 2, is equal to n times the natural log of 1.07. I can then rearrange it because I want to solve for n, and I bring the natural log of 107 to the other side, and so n, the doubling time, the number of years it'll take for my investment to double, is equal to the natural log of 2 divided by the natural log of 1.07, which gives me 10.24. Again, any calculator worth its salt or spreadsheet, you can use this ln or natural log function, or if you wanted to, you could stay with log base 10. It doesn't matter. The logarithms, regardless of the base, have the same properties. Just make sure that you use it consistently within the same equation. So I could do log of 2 divided by log of 1.07, and it would also give me 10.24. So essentially, what does this mean? My investment will double in value in 10.24 years if I have a 7% annual interest rate. So that's great. We answered this question for a given interest rate of 7%. Now, maybe I want to come up with a generalized form. So can we come up with a general equation or an approximation for if I give you an r, you tell me the doubling time? And so we know that t, that doubling time, is equal to the natural log of 2 divided by the natural log of 1 plus that r, that interest rate. If I plot that, where I have t is a function of r, so the x or the horizontal axis is the r, that interest rate, and the y or the vertical axis is the number of years it takes to double in value. If I plot this for different values of r, look what it does. It just goes out in this nice little form which we've seen before, right? It's a power function where y equals a times x to the b, where b is less than 0. So we want to find this value where t is equal to a times r to the negative 1, or t equals a divided by r. And so plotting this out, you can fit a curve to this and see that this A value would be equal to 70. So we're saying the doubling time is essentially approximated by the number 70 divided by my interest rate. So doing this, and interest rate here is written as an integer. So our 7% would be 7. So you see that our doubling time, t equals 70 over 7, gives me about 10 years. So it's a good approximation. And it's all about fitting this curve. So what we've done here is showed how you can use logarithms. Yes, they can be a little abstract, but they're very powerful. They're just the inverse function of the exponential. Just like division is the inverse of multiplication and subtraction is the inverse of addition. So again, another tool in your mathematical tool belt that you will find very useful later on in the course.